Dima? Oh, Joe, can you see me or what do you see now online?
Yes.
So do I need to present through Zoom
Yes.
the slides?
Yes. You need to share your screen on Zoom. Of course, you need to share your screen on Zoom, but you also share your screen normal. So where are your slides?
This is. Holy crap.
Who disabled share?
No, I didn't. You're the host now.
Why are you here? Why are you not in Zoom? Open Zoom.
No, but here in the meeting, right? You're the host.
You're giving me the full host?
Yes, you're
I need
host.
to give it back.
No, you can just enable. This is just so complicated. Why are? Shall we just not do this?
new things are still necessary. Kinetics, similar story, big improvements. We identified good models and good training ideas, but also now at 90%, possibly also noise level. So back in 2021, we started thinking, okay, how can we build a benchmark that evaluates more general perception abilities, not just vision, also audio, text understanding, that has many tasks, such as classification, that is challenging for years to come, that has new videos, people are training on the whole internet, there's lots of checkpoints that have seen the whole internet, so it's always good to have some new fresh data on which we haven't yet been trained on. Also, we lot of designing videos that are especially challenging for evaluation, so we can create complex situations that are very hard to find online. Something where anyone can quickly evaluate their models on, no matter how many computational resources they have, and also importantly that it's ethically collected and owned. So we have videos won't disappear over time. There will be no legal challenges that involve always with everything. We paid people to create them, and then we own them, and we made them public. So our first release was like 1 year ago, October 12th. Yep. And then we had a little workshop a couple of weeks later where we had some feedback, how to, ideas about this benchmark, what's wrong, what's right, how to improve it. So that was last year. And eventually, this year, we published the paper at the RIPS, the perception test, the diagnostic benchmark for multiple video models.
Laptop.
And and we created this challenge that has 6 different tasks. The interface at eval.ai is from here on the right. And we have prizes of 15K total. And we were very happy. We had great participation. Around 100 teams registered. We had 500 submissions across all the tasks, and we had like really large improvements over the baseline. For example, with multiple choice QA, our baseline around 55%. It went to 70%, so huge improvements for the first challenge. Also, very large improvements in action localization, sound localization. And so this is the program. I'm doing this introduction. We'll have an overview of the perception test by Björk next. We'll have a talk by Derek Hoyen. Then we'll have a little coffee break, maybe not as long as John side of the day. Then we'll have finally the overview of the challenge and the announcement of the winners. We'll have talks from the winners. Then a talk by Rodin Kirtar. And we'll finish off with a round table and closing note where we want to get some feedback from participants and anyone winning. So we also have t-shirts right there for winners and anyone here participating in the sessions or asking questions. So probably coffee break, you can here or at the end. And so we also have a website where you can write questions. So there's this QR code here. If you want to post the questions online and see other questions from people that are remote. And this was the team. It was a big effort, some 2 years of work from lots of people. And I'll skip to Gary.
Okay, so hello everyone. So I will give a brief overview of the perception test, the benchmark that we've created. So as Raul mentioned, we are seeing impressive progress towards building actually general perception models like Flamingo or Poly or GPT-4 and others. And this is a clear departure from specialized models in computer vision, like object detectors, object trackers, image classifiers, and so on. So these are actually systems that can perform new tasks by seeing just a few examples or perform tasks in zero-shot setup. So these are really impressive systems. However, we know that they're not perfect, and when we interact with them, we can see that we can see some weaknesses. So, for example, in this video, it's playing. Okay, so it's a simple video. I think if what do we see? We see a person making a tea, and then they do something funky with a slice of bread. Now, if we ask, for example, Flamingo what it sees in this video, it says that the person is making a sandwich. So that is not really correct. And we can go on and on to test these systems with various examples, and we see that sometimes they have an impressive performance, sometimes they fail. However, to actually improve these systems, we need a quantitative evaluation to see where their strengths and weaknesses are. However, there is no such thing as a general perception benchmark. So there are lots and lots of benchmarks actually related to perception in our community. So a brief look on papers with code will reveal that we have by modality, for example, related to perception, we see there are more than 4,000 benchmarks, and we can see where the community has put the focus. For example, we have lots of benchmarks on related to images, and then less on video, even less on audio, very few on 3D and speech, and so on. And we can also look by computational tasks, and we see that there the dominant task is semantic segmentation, then object detection, image classification, and so on. So there are really a lot of benchmarks. However, the one thing that really unifies all these data sets is the fact that they have all been built for training systems. So we have these systems that are very data hungry. So people have put a lot of effort into collecting training data sets. And we need them to be large scale. We want them to be diverse. If we can collect labels, that's great, with various levels of noise. And then the source of data is either from online repositories or they're crowdsourced. And then how do we do evaluation? This is generally just a split of the training set. So there is one issue, important issue that we've started seeing recently about this, going with this approach, is that when we do in-data set evaluation, there's actually a lot of benchmark overfitting. So there are papers that show that your model, when it's evaluated on the data set that comes from the same distribution, it performs actually much better than when you go and test on another data set. So this hints that we need to do something about it. And another issue with the existing benchmarks, even though there are so many, is that there is this high fragmentation across computational tasks and modalities, which leads to having a redundant coverage of some areas. And this is mainly in semantics. So for example, we have image classification, object detection, image retrieval, and so on. But I claim that all these tasks, they actually probe for object recognition. And while we have overrepresentation of such tasks related to semantics, some areas are actually completely missing in our benchmarks. For example, memory or physics skills or types of reasoning, like counterfactual reasoning, we don't have it in benchmarks. And another issue, of course, that has been studied quite extensively in the community is the bias in these data sets. So we know that there is a gender bias or geographic location bias, and other skin tone, type of content, and so on. So the goal in our benchmark, in our project, was to design a comprehensive diagnostics perception benchmark. And kind of the directions or the points that we wanted to make sure we respect is we wanted the benchmark to be comprehensive, so to have very good coverage of different skills that the model should have. We want to limit the bias. Ideally, it should have no bias, but that is very difficult. So we want to limit the bias as much as possible by ensuring diversity of data and of tasks that we include in the benchmark. Then we want the benchmark to have a good predictive power, meaning that when we see improvement on the benchmark, we want this improvement to correlate with improvement in real-world operation, because otherwise it doesn't serve much to just maximize the number on a benchmark if that doesn't translate to actually improving a model that is improved for real life. So to have this kind of predictive power, we focus our evaluation on strong generalization. So we want the system to be evaluated in 0-shot or a few shots. And then we also want the evaluation to be efficient, meaning that for example, we could have taken all the data sets that we have and just create a very large evaluation set, but that would not be very efficient, plus the coverage issue. And ideally, one might say, well, we can just put humans in the loop and evaluate the systems like that, but that would be very expensive to actually have. So the approach that we took in designing our benchmark is that we started with a list of capabilities that an ideal perception model should have. And then we looked what kind of in what kind of videos can such capabilities be tested. And then we collected the annotations that would allow testing for those capabilities. And this was the list of capabilities that we came up with. And in choosing these capabilities, we took into account multiple factors. So first, from our experience, we know where current models fall short. So we know that they're not good with memory-related tasks. So long-range temporal dependencies, models struggle with that. We also know that models struggle with physics understanding and geometry, tasks related to understanding spatial relations, containment, or motion, fluid interactions, and so on. And then from measuring intelligence in humans, we know that abstraction is a very important area or capability for humans. So we try to include those kind of tasks as well. Like, for example, discovering patterns or discovering pattern breaking. And of course, we also have an area related to semantics, because semantics are important. A model needs to know semantics to be able to interact with humans. And besides these capabilities, we wanted these capabilities to be tested through different types of reasoning to have a thorough evaluation. So descriptive, explanatory, predictive, and counterfactual. And these are inspiration from cleverer data sets. So next, once we settled on the list of capabilities, we looked at what kind of videos can allow testing for those. So they should be perceptually interesting videos to be able to test the skills. We want to have a balanced and diverse data set. We want to enable both language and non-language tasks. And we want to be able to assess high-level understanding to lower-level tasks or the other way around. Like, we don't want to impose that the model should have language capabilities. So we can go a long way with just an object tracker, for example, if it's powerful enough. So by looking at this, we concluded that actually YouTube videos are not suitable for such an evaluation, because some types of data are simply not available on YouTube. So for example, if you want to probe for action, like correct action completion, you will find a lot of videos on YouTube, but not many will show a person that doesn't tie their shoes correctly or doesn't button their shirt correctly. Normally, all the videos that are out there, they show correct executions of actions. So we decided to design scripts and film them with crowdsourced participants to be able to tick all the boxes that we want. So in designing the scripts, we took inspiration from a few sources. So first, we looked at perception tests for humans and the kind of props that are used in testing perception for humans. So for example, letters or geometric shapes are widely used because it's easy to refer to them, and then it's easy to ask a lot of questions about spatial relations and counts and so on. And then we looked at existing work in synthetic data sets, because there are a couple of works that have done very good job with coming up with diagnostics in the community, for example, Cater or Cleverer. And then, of course, we looked at existing real-world data sets that have used videos collected on demand. And there are several such data sets. So, for example, when talking about how to ethically collect videos, we took inspiration from Epic Kitchens by informing users and having the explicit consent. Then having diverse participants and geolocation. Well, it was the same that was done in charades or Ego4D. Various aspects related to diversity of objects, camera viewpoints that were used in something or charades and so on. So we took inspiration from all this and we tried to have everything in one place. So the script design, the script that we came up with, they show very simple situations actually. So to test, to probe for perception skills, we don't need very fancy videos. Actually, simple situation and games, they are very good to probe perception. So we came up with such situations, and they can be performed by any one person. So we don't need professional actors. And we shipped some objects to this person, like letters and shapes, so they can film the scripts. And we designed multiple variations per scripts to make sure that we have very good diversity. And for privacy reasons, we instructed participants to not film their face or to not speak. And the focus was always on the hands and their interactions with the objects. And to make, as done in other efforts, to make the videos more interesting, we use distractor objects, distractor actions, and the adversarial object configurations, adversarial actions, and so on. So this is kind of how a script would look like. So we have a small description of the scene, then a short description of what the action should look like, and then what should happen with the camera. So this is a very loose definition of the script, so we didn't want to go too strict because we wanted to leave a lot of room for variability and creativity to really collect a diverse data set. And these are some examples of the collected videos. So as I mentioned, we have different variations per script. So here are some examples of scripts with two variations. So on the left, we have positive and negative variations of the same script that is used to assess stable configuration. So you have people putting objects on top of each other, and normally when we evaluate, the video at the bottom will be chopped before the person puts the last object, and then we ask, is this configuration likely to be stable or not? Then on the right, we have a script that assesses task completion. So again, positive and negative. At the top, you have a person that matches correctly the lids. At the bottom, they don't match correctly the lids. Another example of script with 4 variations this time. So here we have cup games, which are very useful to probe for understanding of object permanence or understanding of motion through occlusions, object solidity, and so on. So here, the variations that we considered are in terms of number of objects, or if the objects are identical or not, if the camera is moving or not, and so on. So once we collected the videos, and yeah, I should say we collected in total around 11,600 videos with audio, and they have up to 35 seconds length. So once we collected the videos, we annotated them. And in choosing the types of annotations, we want the annotations that enable evaluation of low-level and high-level understanding across different space, time, and modalities using both language and non-language interfaces. So we settled on this 6 types of annotations. So we have objects because we considered objects as the root annotation in our system. Objects are really central to perception. Then we also collected point tracks to be able to really probe for understanding of object deformations in time, tracking object surfaces. Plus, to cover the temporal aspect, we collected action segments. Then to go in the multimodal space, we also collected sound segments. And just to say, both action and sound segments, they are also grounded in objects. So we have the annotations are linked to the objects that are involved in actions and sounds. And then we have the multiple choice video question answering and the grounded video question answering. And I will show some examples just to see the definition of the tasks. So I mentioned the existing data sets that we use for inspiration. This is just a quick comparison with those data sets. So we see that in our data sets, we have the widest coverage of skill areas, so memory, abstraction, physics, and semantics. And we have the highest density of annotations. So we have the different types of annotations that I mentioned on the same videos. So we believe that this can enable actually very nice elements. For example, we could have more efficient evaluation, where you could imagine that we extract feature once, and then we query with many different tasks. And it can also enable a more detailed analysis of model performance. So for example, we could look at the performance of a VQA model if it focuses on the right objects by using the object tracks that we have. So as I mentioned, all the annotations are related to objects in one way or another. So to show examples, so these are the object annotations. So they are collected at 1 frame per second rate. Here I'm showing only frames that have human annotations. The videos themselves are high resolution, temporal resolution. Then, oh, these were supposed to be the points. What's happening? Okay, sorry, I'll go back. Oh, sorry about that. So that was supposed to show a video with the objects and points. Sorry. This is a video showing objects and actions. So as I said, the actions, they're labeled with a start and end time, and then they're also grounded in the objects that are involved in those actions. Then for sounds, oh, okay, that's no problem. So for sounds, we have similar as to actions. We have the start and end time of the sounds with the objects involved. And then for grounded VKA, okay. It's the internet. Yeah, I think it's from Zoom, because this is presented through Zoom. Sorry about that.
Can you play when it's not maximized?
Yeah, this is what I'm trying. Okay. Let's see. Inject some points.
Try playing. Yeah, that's it. Okay, plug it in now.
Okay.
Plug it. No need to ask again.
Okay, let's try again. So the objects points. Yes, we have the points. So as you can see, we have point tracks that follow the surfaces of the object. So if the objects rotate in space, the points will move with the object, while the box will not show that. Or if the point becomes occluded, we also have an occlusion flag. So all these things you would not get from just a box track. So actions, we've seen the actions. So as I said, we have the start and end time of the actions, and then the objects involved in those actions. And here they are shown only when they are actively involved in the action. And then for the sounds, if this works, the sound, let's see. So again, we have start and end time of each sound segment, and then the objects that were involved in creating those sounds. And the types of sounds, so we have objects hitting each other, objects, sounds of pouring liquids, or clapping hands, and so on. And the examples that I wanted to show for grounded video question answering. So here the question is given in language, and then the output is a list of object tracks in the videos. So this is really a way to connect a high-level interface like language with a low-level understanding. We are really probing for object tracking and localization in the video. And as I mentioned, we are interested in strong generalization in our evaluation. So we put most of our videos in the validation and test splits. And we still provide a small training split just in case if the models really need to use it to adapt to the task. So as I mentioned, in total, we have more than 11,000 videos with audio. And yeah, these are the splits. And ideally, what we would want to see, the kind of evaluation setup that we want to have is where you just bring in your pre-trained representation, and then we can probe it on all these different tasks, ideally in zero-shot setup or by showing a few examples from the training set. So because no model can currently perform all these tasks, we included per task baseline. So for object tracking, we used a SAMFC tracker. Point tracking, we had TopNet and so on. And we noticed that the performance is actually not that great for most of these models. So this is a very challenging benchmark. And I say, especially for grounded VKA, the performance is very poor. There is, even for this task, actually, there is no baseline in the community. So we improvised one by using MDetector to detect objects on the middle frame and then propagate those detections in time using an object tracker. And just to give some examples, more details about the evaluation in the multiple choice track, because like the recent models that I've shown that are very powerful, they are video language models, so they can perform this task out of the box. We evaluated here Flamingo and Sevilla, and for Flamingo, we tried zero-shot and 8-shot, and for Sevilla, we tried the zero-shot and fine-tuned. And we also collected a human baseline for this task, and we can see that the human baseline in blue, they are close to perfect. So the number is 94.5%, whereas the models really struggle. Here in black, we can see the random performance, and we also have, sorry. So I just wanted to mention, for example, if we look on the right, so Flamingo in red, for example, is worse than random on counterfactual reasoning. So this really points to a significant weakness in the model. And more detailed for fine-tune for Sevilla, I mentioned that we fine-tuned it just to see how far it can go with fine-tuning. The number did improve overall. However, when we check in detail over the different skills, we noticed that actually Sevilla just manages to extract the frequencies from the data set. So we also have this frequency baseline. So because in our data set, we have multiple choice question answers, and one question is applied to multiple videos. We can compute a blind frequency baseline that just looks at the training set and picks always the most frequent answer from there. So the fact that this frequency baseline does better than random shows that our benchmark is not perfectly balanced. And this is a problem. However, it's very hard to have perfect balance there. But what is important is to keep this in mind and consider this when we analyze results. So we can see that actually fine-tuned Sevilla actually gets a bit better than this frequency baseline. So it just extracts these frequencies from the data set. And I mentioned that that the diversity of participants was an important aspect in collecting the videos. So here are some numbers to show the diversity across gender, ethnicity, and countries. So we had in total more than 100 participants that filmed our videos in these different countries in the world. So we chose to have these different geographic locations to make sure that we have diverse objects plus diverse skin tone. So we could have gone, like, for example, to US and collect all the videos there, because we can get skin tone diversity, but then we wouldn't have the geographic diversity. So in summary, the perception test is a benchmark that contains purposely filmed videos to test perception. It includes low-level and high-level tasks across video, audio, and text modalities. It enables language and non-language evaluations, and the focus is on strong generalization, so zero-shot and few-shot evaluation. And we really hope that this benchmark will guide research towards improving models' performance in physics areas, in memory and abstraction. But I just wanted to mention that the Goodhart's law, when a good measure becomes a target, it ceases to be a good measure. So I think in general, we should think of the role of benchmarks as being guiding for research, and we shouldn't just try to maximize the number of the on the benchmark. And these are a couple of examples to finish off. So these are videos from the benchmark with the kind of questions that we have. You could get a T-shirt if you answer correctly this question. So you see this video, and then the question is, what might the person do next? I'll play the video again in case you didn't pay attention. Okay. Any guess? Okay, okay, yeah, there. You have a T-shirt. In this video, I mentioned that we have adversarial configurations of objects. For example, you see this water bottle on top of a shoe, on top of a table. This is not a normal configuration of objects in the real world, but we wanted to have such configuration so that we can probe the model's understanding of spatial relations without language bias, because or without the bias, normally chairs are always under the table or next to the table. Cups are always on top of the table and so on, but we wanted to have these weird configurations to see if the models actually understand the relations between objects. Another example. Okay, so the question, does the launch object fall off the table at least once? I hope we agree that it didn't. I am not giving a T-shirt for this one, it's too easy. Just to mention the question that we saw before with the claps and no claps, that is a question in the abstraction area. So there we probe for understanding of patterns. And here, this is understanding of physics, because the object becomes occluded, so we asked, did the object fall off the table? So it didn't fall off the table, it just became occluded behind another object. So just to say, we always have 3 options for all the questions. So sometimes you'll see I don't know as an option. However, that option is almost never correct. So Sevilla did detect that. So it always chooses yes or no. It doesn't say I don't know. Okay, so this is the end. I don't know if there are questions or if we have time for questions. I think Joe announced that if you ask questions, you might receive a T-shirt. So, yeah.
Obviously, feature isn't deterministic. For the hard packing example, the feature isn't deterministic, so any one of those answers could be incorrect, could they? So what might they do next? Yeah. So, yeah. So any of them are strictly correct, that you're saying.
Oh, sorry. So in this case, that's why it's important to have the options as answers. So now you need to choose one of those options. I think it would be, like, sure, I don't see why you'd say, oh, the person might clap 10 times. Or the idea is to detect the pattern and to find the simplest explanation.
This is prompted explanation of the
Okay, yeah, I see your point. Yeah, we didn't prompt it explicitly, but that's the point, that it should find the simplest explanation of what would happen next in the video. Yeah. But it's a good point. Yeah, maybe we need to explicitly mention that in the prompt.
Thank you very much. It's been really interesting to hear these explanations. But I'm also wondering, given that, first of all, there were scripts, I presume that they were written in the natural language. So there were a few questions which I thought might be quite important for me to clarify. So with the language annotations, as far as I understand, there were some, right? So all those annotations were, I presume, in one language, perhaps English, right? And then also, given that it happened across different countries, was it all scripted in English? And obviously, across the countries, people have different dialects of English and different understanding of English, different levels of English. So how did it affect the performance? All that sort of intersection between the language commands, language annotations, and language understanding between humans.
Yeah. So indeed, all the scripts are written in English. During data collection, we checked the videos to make sure that they respect the scripts. So we did encounter issues with people not understanding the script. So then we would just go and explain again the script, what it should contain. So yeah, the videos were not showing what they should. Then for the annotations, we designed the questions, and we designed the questions with the options, and then gave to people to answer those questions to make sure that all the aspects are clear. And I realize maybe they're not all very clear. We can still improve, but we designed our research team designed the questions and the answers. So and then when we ran the human baseline, we noticed that there was no problem with the understanding of questions. Like for humans, it was really very easy to do the questions. Like we didn't need to train the humans. Like the questions are so simple that they didn't need any training. So humans are zero-shot evaluated here.
Thank you very much. That clarifies it.
Yeah.
Thank you.
Hello. Is there any merit of using the perception on like a single modality as a unsupervised model, like another stuff like that? What would you say?
So for anomaly detection, I imagine it's again a problem of finding a pattern, or but yeah, maybe it's a bit more specific. Yeah, I'm not sure like what kind of anomalies you're thinking of.
Okay, let's say like or like let's say it's not anomaly. So for instance, I would find and find pattern that's deviating from any so is that something
So we have this task of detecting patterns or breakage of patterns. So I am hoping that if we have a model that actually does well on the perception test, it will do well on the type of pattern that you have in your downstream task. But we still need to test this and see how. But I think what is really important is that the evaluation is done zero-shot, because if you fine-tune your model on this, then it might answer correctly our questions, but there won't be a guarantee that it will do well on your task. So that's why I think it's very important to probe in zero-shot. Okay, so maybe we move on. Thank you.
Zoom, or how do we do it? Go ahead.
Okay. Oh, I need the microphone.
All right, it's our great pleasure to have a keynote speech from Derek Hoyen now.
I have no idea what this is.
Well, while we sort the slides. So Derek, he's a professor at the University of Illinois at Urbana-Champaign. He's also co-founder of a company called Reconstruct. And he's been a star for a long time, since his PhD, very early on. So he did this very interesting work on the interplay between reconstruction, recognition for scene understanding. And it was the main game in town back then. He got all possible awards since then, and recently started working on general perception models, hence our invitation to speak at this workshop. And yeah, without further ado, Derek.
All right, thank you. Thank you for the invitation. It's an honor and pleasure to speak here.
Might need to click on the slide.
Okay. Yeah, so I want to start with the business adage: what gets measured gets done. This is often attributed to Peter Drucker, the management by objectives guru. And the idea is that if you really want to accomplish something with your organization, then it's necessary not only to state what your goals are, but to figure out how you're going to measure it, and then to begin to measure and track it. And if you do that, it creates accountability, and it will lead your organization to work towards those goals effectively. Now, of course, it's also a double-edged sword. If you start to measure things that are not that useful, then you can cause your organization to try to optimize those things that are not quite so useful. And of course, this applies not only to business, but to the research community. Our benchmarks and evaluations are not only a reflection of our research, but they drive our research for better or for worse. And so it's worth taking some time to think about the evaluations that we've created, what evaluations we should continue to do, and what breakthroughs are needed. And so that's what I want to do in the talk today. So first I start with the evolution of evaluation. So we can look to see how evaluations have changed over time in computer vision. If we go way back to the 80s, we tend to see evaluation by single examples. For example, with the Canny edge detector or with Lucas Canati. Often in these methods, they had strong theoretical and principled underpinnings. And so in some ways, it wasn't necessary to really thoroughly evaluate. You could prove why the system should work, and then you show on a few examples that it does work, and that's often enough. And of course, these algorithms are well used even today. Then as our algorithms started to become more data-driven, as it became necessary to learn from data and not only to derive our parameters or derive the algorithm, then it became necessary to evaluate in a more systematic way how well a system performs. And so we started to have evaluations like the MIT plus CMU face data set for measuring face detection. Then there was also a data set soon after for evaluating car detection, sometimes in multiple poses. And at this time, the evaluation focused on a very narrow task of trying to detect a single object or maybe classify among a small number of categories. The next stage of the evolution was in multi-class evaluation. And one of the best of these benchmarks was the Pascal VOC by Mark Everingham and colleagues, where the evaluation featured many different object categories. And the idea was that you should start to build detection and classification and segmentation methods that are not only particularly suited for a particular category like faces, but are suitable for a wide range of categories. And then we started to evaluate as an average precision or mean average precision, averaging across the performance of many different categories. Then we've started to see more multitask evaluation. So for recognition in the COCO data set, you have panoptic segmentation, key point prediction, and other tasks. There's benchmarks like the Blue Vision Language benchmark that's kind of inspired, I think, by the GLUE benchmark, the General Language Understanding benchmark in NLP. There's cross data set evaluations like the Robust Vision Challenge, where you need to demonstrate that your system can perform on a range of data sets on a particular task like depth estimation. And then there's also, it's commonly used, many methods use multi-benchmark evaluations in the papers. And then this has started to evolve to novel task and concept evaluations, where you tend to have more held out benchmarks where you may not have a training set, or you're limited in what you can train in performing those benchmarks. So a couple of examples are the grit and perception tests, which you just saw. So if we look at this really broadly, then from around 1980 to 1995, I would say the evaluation mainly focused on showing that a system can work. You may show on a few examples that here I have an algorithm, this is why it should work, and look, it does work on these examples. From 1995, and I think this will continue to be important for a while, the evaluation is how well can it work? So we tried to more systematically evaluate to quantify the performance of a system. And so what would come next? Well, I think the next phase of evaluation is going to be on how much effort is needed to make it work well. I think that we'll start to take for granted that it's possible to make a system work well on a given task. But really the question is, how much effort do you need to put into it? Because what becomes important as we put these algorithms and methods into practice is that many users have their own particular tasks that they want a system to perform. And the cost of the system is really how much time they need to put into it, how much computation it requires, how much data, how much work they have to go through to get the system to do what they want. So we can look at evaluation in two different ways. There are two different broad kinds of evaluation. One is an evaluation of what can it do, which again is what current evaluations have mostly focused on. And we can look at the accuracy of a system, its calibration, whether it's able to produce good confidences, robustness, generality to across domains or imaging conditions, ability for zero-shot class or task prediction. We can also start to think about how well can a system learn? How many examples does it need to learn a new task, a skill, or concept? How long does it take to integrate new information into its models? Is it able to retain past concepts and tasks while it learns new things? And is it able to learn from many different kinds of supervision or many different modes of learning? So before I jump into how we can start to think about evaluating the learning capability of a system, I do want to emphasize the great what can it do benchmarks. And I think, although I won't go into any detail here since you just saw a lot about the perception test, I do want to emphasize that I really love this benchmark, and I think it's a great benchmark for helping the field move forward into more general capabilities. And some of the things that I really like about this challenge are the aspects of evaluating skill areas rather than evaluating ability to detect particular objects or evaluating on more narrow capabilities. I really like the inclusion of memory because that's something that is, I think, holding back a lot of AI systems today. The multimodal aspect and the idea of evaluating few shot or zero shot skill and task completion. So it's a really great benchmark that I do think has the potential to drive a lot of good research over the next few years. I also want to touch briefly on another benchmark that I introduced with colleagues from AI2 and UIUC in the last couple of years. And this is called the GRIT benchmark, General Robust Image Task Benchmark. And here we have 7 different tasks, and the idea is to try to create systems that can do all of these tasks. You can just submit to a single task, but the main evaluation is in terms of your average performance across these tasks. And for each of them, we have a few data sets. Most of them were existing data sets. We tried to use ones that are kind of hidden data sets or evaluation, ones that are behind evaluation servers where possible. And some of the data sets were data sets that hadn't been released yet. And so we can evaluate different kinds of generalization and robustness and calibration. So for generalization, for example, there are some data sets that you're not allowed to train on. And then we want to evaluate how well systems perform on the data sets they are allowed to train on versus the ones they are not. For example, you're not in this task, you're not allowed to train on open images, but you evaluate the performance of semantic segmentation on the open images, on some images from open images. We also evaluate the generalization to new concepts. For example, how well can you do on concepts that are not present for a detection task in any of the training data, or that you need to be able to generalize from other pre-training that you do to these concepts in particular skills. We evaluate the robustness to image perturbations and adversarial attacks, and also measure the system's ability to predict good confidences, to evaluate whether the system can say what's the probability that it got the answer correct, so that the system can, whether it knows what it knows. And so the idea is that by submitting like a single file for these tests, you're able to evaluate a broad range of the capabilities. Its generalization across different data sets and concepts, the robustness with respect to various perturbations and attacks, and the calibration ability of the system. So I think these kinds of evaluation in terms of what can a system do is continuing to improve. And it continues to be, I think, what will drive like vision forward in the next couple of years. But again, like as vision continues to evolve and be deployed, I think finding new ways to measure learning ability becomes increasingly important, so that we can try to create systems and methods that are adaptable to a user's needs. So the first question is really what makes a good learning system? And I would say that a good learning system is efficient. It can acquire expertise from few trials or examples. It's flexible. It should be able to learn opportunistically from many sources. It should be anytime, in that it can add and use new information in real time. And it should be cumulative. It should be able to gain new abilities with minimal disruption to the existing abilities. So evaluating these kinds of learning abilities is kind of tricky. So with humans, when we want to evaluate a learner, we tend to give them an exam. And the same when we want to evaluate a classifier or a vision system, we give it a kind of exam and we measure its performance on those tasks, or on those examples. But these are measures of what has been learned, not really measures of how good the learner is, like how capable the learner is. So we may want to measure, for example, is the learner efficient? Are they able to learn quickly over many examples or over time? And how well would they do if they were able to get more data, or if they had less time to learn or fewer things to learn from? So one of the ways that we started to look at this recently is with learning curves. So we can model the test error as a function of the training size, just by varying the number of training examples, estimate the test error given that number of training examples. And you can fit parametric curves to these, you can plot those points and then fit parametric curves to them. And we can characterize them in terms of a data sensitivity, how quickly the system gets better or worse as you change the number of training samples, as well as the error at some training, at some number of training samples. And we show that you can evaluate various aspects of the learning. So you can look at what's the effect of the pre-training source, what's the effect of the optimization method. We can also look at the effect of network depth, network width, the data augmentation, and various other things. So this kind of lets you look at how a design decision or how some method enables this or changes the learning characteristics of a system, how quickly it learns, rather than just like how it performs on a particular benchmark given all the training samples. I would say that this can be really useful if you're introducing a new optimization method or trying to evaluate something very generally, but it may be a bit cumbersome if you're trying to evaluate on many benchmarks. And so there's other ways that have been used recently to measure learning efficiency of various forms that I think are good to broadly adopt. So one of them, so if you look at, you can find some examples in the CLIP and Dino papers. So in CLIP, for example, they measure 0-shot versus 1-shot versus few-shot versus n-shot performance on a variety of benchmarks. Dino measures performance versus pre-training size, performance versus model size, and performance versus the amount of tuning. So these are all measures of learning efficiency, how many data samples you need to achieve some performance, how much pre-training data, how does the performance vary with the number of parameters and with the amount of tuning that you do. So these are all looking at how much data and how much computation and how much complexity is needed to get the system to learn something new. Beyond the efficiency, we could also try to think about how do we measure the flexibility of the learner, its ability to learn in a variety of different ways. So you may want a system to be able to learn from examples, from demonstration, from exploration, from instruction. And having this variety of ways to learn creates many opportunities for learning and can lead to much more robust systems. So I don't think that there's any benchmarks out there that can evaluate this kind of breadth of capability. But one idea is to create a kind of learning style decathlon. So you could have the same task and supervise that same task in different ways. For example, you could provide instruction, you could provide examples or demonstrations of performing the task. You could have a more unsupervised or feedback-based instruction or feedback-based supervision where the system's allowed to perform the task and it gets feedback on whether it performed it successfully or not. And then it would be interesting to see like how well can a system perform under these various kinds of supervision or using combinations of them. So we would also want a system to be able to do anytime learning and cumulative learning. And here we might want to measure how long does it take to learn from a single example and can it learn new skills and concepts without fully rehearsing and without forgetting. So recently we've looked at these things in a paper that's inspired by the complementary learning systems in studies of the human brain. So the idea is to combine deep models that are able to slowly consolidate information over time with sparse exemplar-based models that are able to quickly adapt and integrate new information and then make predictions based on a combination of these. So the method here is not particularly important to the talk, but some of the things we look at are like how well the system continually improves while retaining 0-shot ability as you add new tasks or as you get data in like a random order. So data incremental, task incremental, or class incremental as you see tasks in a random order. And then we also look at how long it takes to learn a new example in terms of time. So if you just get one new example and you want to update your system to that one new example, how long do you have to wait? With a lot of methods that are based on deep learning, you would need to basically like cycle through a lot of your data in order to integrate that new sample while retaining your current abilities. And a method that we propose is able to update in constant time. So I think it's starting to become important to think about and measure these things. So in summary, we can measure the learning ability in terms of efficiency with respect to data, model size, pre-training, fine-tuning, flexibility with respect to the different modes of learning, learning from example or demonstration, learning from feedback, instruction. And we can measure its ability for continual learning with respect to the speed to incorporate a single example or to continually improve. And the final question I want to ask and partially answer is what breakthroughs are needed to create better learners? So as we start, if we do create these evaluations and as we start to measure the learning ability in new ways, what are the technical achievements that we're going to need in order to improve in these measures? I think here the key is to really focus on memory. So we tend to think about things in terms of architectures and in terms of data, but thinking of it purely in terms of memory can be helpful because learning is really just modifying memory, and intelligence correlates to how versatile, agile, capacious, and organized is your memory. So we need, thinking about it in terms of memory, we want to think about how can we achieve these characteristics of the system's memory. And I think we can get some hints if we look at the differences between human memory and AI memory. And one of the big differences is just the level to which human memory is very heterogeneous. There's many different kinds of human memory that need to work together in order to learn and accomplish our tasks. And I think that's not an accident. I think it's very important for creating more flexible and continually learning systems. So in humans, for example, we have a sensory memory that's very brief, just for maintaining the information that we're currently observing. We have short-term memory up to 20 seconds, including a phonological buffer, a sketch buffer, and working memory. We have long-term memory, and we have two main kinds of long-term memory. We have an explicit retrieval-based memory that recalls specific instances, can be episodic, and it has a sparse structure so that you can quickly update it without overriding or interfering with your memory. And then we have a more implicit response-oriented memory that's consolidated. It has a dense structure, it's slowly updated, and it's ever-changing, and so it's prone to forgetting. And then we also have, although it's kind of up for debate whether this is actually like a property of the kinds of things that we're remembering versus a structure that's innate in the brain. But there are specialized memory areas for faces, places, and there's a procedural memory for learning tasks. So there's a really complex set of different memory systems that work together to give humans all of the capabilities we have to wake up, learn something in the morning, use it right away, integrate it into the rest of our memory to generalize and so on. On the other hand, with AI, we tend to have homogeneous systems like a bunch of transformer layers. And this may have like a couple of kinds of memory, a working memory. So there's a really interesting recent paper, Vision Transformers Need Registers, showing that transformers will actually like kind of commandeer certain visual tokens and use it as short-term memory. And as a result, produce tokens that are not very predictive, but are useful for the system. And then there's a long-term implicit memory in the form of MLP or attention weights. This is really very simplistic compared to human memory, and I think is one of the weak areas of AI right now. So human minds are really seeded for flexibility and growth. Our system is designed to learn and adapt to new things very efficiently, while AI minds are molded for task proficiency. We've for a long time been in a mindset of that you take all your data and then you spend a long time integrating it into the system, you freeze the parameters, and then you deploy or test it. And so I think one of the things we need to do is change that mindset to think about learning as a continuous process that happens at the same time that we're performing actions and observing. So some of the major challenges for the next few years are, one is anytime learning, the ability to receive new data in any order at any time, and to quickly use the new information and continuously improve. A second challenge is to create any form learning the ability to learn from all of these different kinds of supervision, examples, exploration, demonstration. And then third is to investigate ways to create multiple memory systems so that we can retain memories of episodes and interactions, learn perception skills and concepts, learn to do more complex tasks, and be able to manage the flow between these different memory systems. So I want to close with another business adage, always be closing. And that's from Glengarry Glen Ross. And the idea is that for a salesperson, anytime that you're interacting with a client, you want to be thinking about how you can close the sale. So the question is, what should the mantra be for us as visual learning researchers? And for us, I think, or for our systems, the mantra should be always be learning. So we need to think about how do we create systems that do not just learn as a kind of pre-process, but are learning during their entire lifetime, that are continuing to learn as they observe and as they perform tasks. If we can make systems that are always be learning, then these systems will be able to perform amazing new tasks and be useful in amazing ways that are currently not available. So thank you very much.
Fascinating talk, and I'm glad I can come to my dad. I'm now building out of it. I have a question about this feedback thing, which has been bugging me for a while. The success of the idea that the models will get feedback and adapt accordingly, and the lack of metrics for how we can measure how these systems are using that feedback, whether they make a mistake again, or how that influences the whole idea of benchmarking. And you touched on it a little bit, I'm saying, the efficiency. Can you say a little bit more on how you see this notion of feedback and its interaction with other people?
Yeah, that's a good question. Yeah, there's it's kind of this may be a little bit of an indirect answer, but one of the things I've been thinking a lot too is that as our systems get more sophisticated and as it becomes more important how they work in the context of collaboration with people or how people are using the systems, our evaluation becomes, I think, like automated evaluation becomes more and more challenging. For example, there's some systems in voice, or some companies that do voice production do not use any kind of automated evaluation for their methods. They instead have people listen to the voice. They have people listen to the voice synthesized results and annotate it in terms of the naturalness or things like that. And so for feedback as well, I think it's a big challenge to be able to automate evaluation of the feedback, especially since that feedback should be custom based on the performance of the task. But it may be possible, yeah, so I'm not sure how to do that, how to do it automatically, but it may also be that small evaluations can be helpful. So sometimes I think, so there's a trade-off sometimes between the quality of an evaluation and the scale of an evaluation. The scale of the evaluation is really only useful in providing a high level of precision on the accuracy or something of a system, but I think there are times that it's not worth sacrificing the quality for the scale, and this may be one of those where maybe having like 100 people provide feedback may be enough to evaluate it. Yep.
You mentioned that but I'm not sure if it's actually event because we want to get on the 12 large we have so I wonder who are the on 12 you benchmark 12 and you might also be
So I think the question is, will building systems that can perform better kind of automatically translate to systems that are better learners? I would say sort of, but not really. Because if you actually go and try to create a product based on today's machine learning algorithms, even though the machine learning algorithms look pretty good and they do well on benchmarks, you'll find that it's a major pain point. It takes typically millions of dollars of investment in order to get a system that seems like it can do something pretty well to do something that's just a little bit different in the application domain that you care about. And so I think to an extent, I think as a byproduct of creating more highly performing systems, you do tend to get systems that learn better in some ways, but I think there's a lot of ways that it doesn't come along naturally. For example, learning from different kinds of supervision doesn't necessarily happen automatically as you improve your performance.
Thank you for that. Currently, a vision foundation models are trained on data, rely on intelligence data sets that are provided. You don't know exactly what the contents of the data are. So it's sort of unclear what generalization to give distribution concepts means at this point. So we are in thoughts how we can design the variation data that are that can be fair to all, fairly assess the performance, generalization performance of all these points. Like, we don't even know what we want to pay on.
Yeah, so I think the question is that it's hard to know what something is pre-trained on, and so it's hard to really know if a concept is new to it, for example, or a particular task. I think that's why things like the perception tests that are test-only benchmarks are really important. They're collected, there are some data sets, there are a few of these data sets or benchmarks that are collected freshly. And so it kind of, you don't know, it's in a way like the other pre-trained systems may have seen these objects before, and that's fine. But since they're collected independently of the system, of whatever these other methods were trained on, I think those provide good tests of the generalization. So basically test-only benchmarks, I think, are the current best way to do this. Okay. All right, thank you.
All right, so we'll have a coffee break until 45.
tracking. First, let's introduce the dataset for this challenge, perception test. The dataset contains 11.6 thousand real-world videos, 23-second average length. The training set contains 2,184 videos. Validation set contains 5,900 videos. Test set contains 3,525 videos. Validation phase, a subset of the validation split of the perception test, containing 1,000 videos.
See, the bunch of them start wanting to pop.
Can you unmute?
I'm in.
You know how to?
Sorry. Is that okay? Yeah. Sorry about that. Yeah, so and then a small piece on the model diversity that we saw across the different tasks. So we provided a baseline for each of the tasks. Where possible, we used like a simple dummy version of a baseline. So for example, for object tracks, we chose like a static where, for example, the box was initialized, and then we assumed a static box across the entire video. Similar thing for points. And then for the localization challenges, we used a network called Action Former that's quite popular. And for grounded VQA, we use like a combination of a detection network, grounded detection network with static boxes. And then when we look at the actual model submitted by participants, there's quite a good amount of diversity across these. So yeah, object tracking, quite a few people who use mixed former, that performed really well. Point tracking, we had quite a few different types of submissions. In action localization and sound localization, actually, interestingly, people tended to focus more on training their own, or sorry, providing their own features
for the network. So they used like the standard action former network, but then they actually improved on the performance greatly by simply using better features or using a combination of video and audio features. And then we had a wide range of different models for the multiple choice part. So also we had like multimodal models here that took in audio and video. We had zero shot and fine tune models. Yeah, but quite a few of these used this severe model, which is quite popular and seems to be state of the art in a few benchmarks. So yeah, a great diversity across submissions here. And yeah, lastly, I tried to show like per task the performance. So all the metrics are normalized between 0 and 1. And then we can see here that we have like quite a tight spread of submissions. So yeah, the performance, especially in multiple choice video question answering and object tracking, was quite high. Also quite a tight spread, especially at the top towards the end of the competition. People really, people were really trying to get that final few points in improvement. So yeah, a really good spread of performance across all the tracks here. I'm now going to hand over to Dima. She's going to announce the prize winners per task. We'll do some questions on the end on anything that I've given. So thank you.
Right. So unfortunately, we are aware that only one member of the team are physically here in person. The others are hopefully online, and we'll be able to cheer them as we go forward. So we'll start with single object tracking. This is the task of given one bounding box, try to track one object. This is such a simplification of the perception test, where the idea is to track all those objects, and we have a large number of bounding boxes per image. But on a starting point, the runner-up goes to the team from Nanjing University, who have achieved a decent performance improvement over the baseline. Congratulations to them. And aha, we have a representation. It's here. We will be hearing some of the talks from the winners before. Thanks, Rimin. And the winners go to the team from Shopline AR Research for the best performance on single object tracking. Congratulations. I don't think there is a representation from them. It's always difficult with these. We will hear a recording performance, a recording video from how they won the challenge. Good. So looking at the numbers, comparing the top performance, so the winners with the static baseline, which was quite, you can see where the performance improvement has been improved, like moving cameras really has changed drastically. So when the camera is moving, we can now finally track some of the objects, but it's always at the expense of the simple baselines, right? So once you have a good simple thing, then looking at cases where the objects don't move at all, you still take a hit, right? Because you're actually trying to do something smart. One of the difficulties in any benchmark is to kind of try to analyze it in a way that we see where performances are gained and lost. Still a while to go. So if you're thinking about this challenge, hopefully in the next competition, lots of opportunities to win. Going to single point tracking, the runner-ups are the team from Zhejiang University, China, and the University of Surrey. Congratulations. And the winners are the team from Nanjing University, Chang University, and Dalian University of Technology. Congratulations. Okay, and looking at the numbers, again, significant boost when we have a moving camera, moving point, right? So this is again where the improvement over the simple baseline, luckily in this case without significant or any clear drop in the simpler baseline, but again, point tracking is still a very, very big significant challenge in perception tests. So plenty of opportunities to improve. Temporal action localization. This is the task of given a known class, find the start and end times of that class in the video. And the runners-up are the team from OpenGV Lab, which I know are here. So let's give them a bigger round of applause. Thank you. And the winning team is the team from China Telecom Corporation Limited, Data and AI Technology Company. Congratulations. We will be hearing from the winning team. Looking at the numbers, clearly you can see the diagonal is best performance prediction versus ground truth, and we're showcasing some of the cases that were clearly biased using the action form or baseline model, which is quite a strong model, still winning some of the benchmarks and other data sets. And this is the top performing model, which is a 0.5 MAA improvement. And this is one particular action, pulling something versus unplugging something. So this is being successfully, this is an error. This is being successfully retrieved. Temporal sound localization. And the runners up are the team from NJust KMG, that's the name of the team, Nanjing University, Riken Center of Advanced Intelligence, Japan, and Alibaba. And the winning team on sound localization, one of my favorite topics. Can you recognize sounds of cups and things hitting one another? And the team from OpenGB Lab has won this challenge. Congratulations. The perception test is one of the very, very few data sets that allow you to look at different set of classes for visual actions and auditory actions. Currently, the two challenges are set separate because we don't have a model that does both, but hopefully we'll have one soon. The multiple choice VQA, this is basically what Viorica has been showing, the question answers, which you successfully managed to do, humans successfully perform. The runners up on this are the team from TG Go Go Go, Alibaba China, congratulations. And the winners are from HS Lab INSPIR, the INSPIR Electronics Information Industry Co. Limited. Congratulations. And we will be hearing, I don't know whether I recorded or a live presentation from this team shortly. Just to see where we are compared to, we've shown you where the performance of the fine-tuned Sevilla, and you can see where the team is improving, particularly on the areas. We see a consistent improvement on memory, semantics, physics, and abstraction. But we do see that this model is still, like other models, suffering on the predictive aspect. Now, prediction is a hard task. So that's one thing we need to look into, whether there are more things in the model to look into or more models to address. And you can look into the report for more details. So this is prepared by Joe on exactly in each particular case where the improvement is. So you can see things like distracting action, distracting object, as well as on the right side, the recognition and the part recognition where there is clear improvements over the baseline. And that's the main idea of the perception test, that we'll be able to go back and see, okay, where are we still struggling and what models do we need to design to do this. And the final challenge is on the grounded video QA. We really struggled to even find the baseline initially for this challenge, as Viorica said, and we're also struggling to get people to try this challenging. As I said, that's the idea of answering the question as well as finding the corresponding object or temporal location. And we do have a best performance. We don't have a runner-up, and the best performance is the team from Nanjing University of Science and Technology. Congratulations. So plenty of opportunities if you want to address grounded video QA. And you can see that, we're just moving above the quite naive baseline that is based on finding an object in an image and assuming it stays static. We have decided to award the most novel submission to the team who went beyond just trying to address one of these challenges. And the most novel submission award goes to Jiangyan University of China and the University of Surrey combined team. Congratulations, and they receive a distinguished special award. And also the most novel team, second award goes to JNU, both Zhejiang University, China, and the University of Surrey. So for those who know Joseph Kittler, we're very excited that he's been in the field for a while. He's found the perception test to be interesting, and he's participated in multiple teams to attempt to solve the perception test in a novel way. Congratulations to all the winners, and allow me also to congratulate the organizers, Joe particularly and Viorica, who have managed to run these baselines and make sure that we are receiving the reports and we can now hear the outcome from the various challenges. Congratulations again.
Because of course I don't know.
So we will be now showing you some recorded presentations of the winners and their answers, their submissions. Okay. Yeah, you put it in. Yeah, okay, good. So display this.
Hello, everyone. Our team name is XWorks, from Shopline AI Research. Today we will introduce a simple solution to perception test challenge. Single object tracking. First, let's introduce the dataset for this challenge, perception test. The dataset contains 11
Sticked, okay. Again.
for videos. Validation set contains 5,900 videos.
We're getting the audio out.
Test set contains 3,525 videos. Validation phase a subset of the validation split of the perception test, containing 1,000 videos and 16,501 tracks. Test phase a subset of the test split of the perception test, containing 1,000 videos and 16,339 tracks. We looked at the data labeled in the training set and found that there are serious labels. There are three main types. The first type of noise labeled box is completely off target. The second type of noise, the starting label box, is too small. The third type of noise, the labeled box gradually shifts. In this competition, we adopt a track model to solve tracking problem. The model consists of three parts: backbone box embedding, neck and head. Among them, patch embedding, shift window attention and LCA constitute backbone box embedding together. The neck consisting of multiple layers of LCAS to refine the state information of the target. The regression and classification head obtains relevant coordinate regression information and classification information from features of search image. Long-term contextual 1. Our team name is XWorks, from Shopline AI Research. Today we will introduce a simple solution to perception test challenge. Single object tracking. First, let's introduce the dataset for this challenge, perception test. The dataset contains 11.6 thousand real-world videos, 23-second average length. The training set contains 2,184 videos. Validation set contains 5,900 videos. Test set contains 3,525 videos. Validation phase a subset of the validation split of the perception test, containing 1,000 videos and 16,501 tracks. Test phase a subset of the test split of the perception test, containing 1,000 videos and 16,339 tracks. We looked at the data labeled in the training set and found that there are serious noise labels. There are three main types. The first type of noise labeled box is completely off target. The second type of noise, the starting label box, is too small. The third type of noise, the label box gradually shifts. In this competition, we adopt a track model to solve tracking problem. The model consists of three parts: backbone box embedding, neck and head. Among them, patch embedding, shift window attention and LCA constitute backbone box embedding together. The neck consisting of multiple layers of LCAS to refine the state information of the target. The regression and classification head obtains relevant coordinate regression information and classification information from features of search image. Long-term contextual attention module is an efficient multi-image attention operation. It can simultaneously perform feature extracting for each image through self-attention and target searching through cross-attention among images. We first compared the three models PartRack, MixFormer, TouchRack. We found that the TouchRack method performed best under zero-shot model. Then, we compared the two online update strategies and found that the meme method performed better. Finally, we add the got 10,000 datasets to fine-tune train one epoch. Table 3 showed that additional relatively clean datasets can effectively reduce the training interference of noisy data. Finally, we achieve average IOU of 0.734 on the test dataset and achieve first place. That's all our reports. Thank you.
So yes, the mention about the noise in the annotations, we are aware that a few tracks are noisy, so we plan to correct that. So unfortunately, this is a recorded talk, so we cannot take questions, and we will now go to the next award for the point tracking, and this is Hong Ping Pan.
Okay, I'm here. Could I share my screen?
Yes, please.
Dear organizers and audience, our team sincerely thanks the organizers for hosting this competition and giving us this opportunity to present our work today. I'm honored to be here and representing the NJUST KMG Point team as we share our efforts and great achievement in the track of point checking. My presentation will be divided into three main parts: introduction, our approach, and experiments. Single point checking plays a critical role in computer vision for tasks such as scene understanding, action recognition, as shown in figures. It entails identifying whether two pixels from different images of the same video corresponding to the same point on a physical surface. But there is a problem. Existing methods often suffer from the cumulative error caused by temporal prediction. We found two issues as shown in this figure. The first problem is called static point jitter, the blue dashed box. Sometimes, even when things are supposed to stay still, they wiggle a bit. But the second problem is static point pseudo-following, the orange dashed box. Sometimes things should be still, but they move because of other moving objects. To deal with these challenges, we proposed a two-stage approach based on TAP-IR model, which is called TAP-IR Plus. It includes two main components, as shown in this figure. Our goal is to fix checking for points that don't move in static camera's video. First, we devised a clever way to tell if a video was taken with the static camera or moving one. We designed a multi-granularity short moving detection algorithm. This algorithm considers both video level and clip level segment analysis. Specifically, we employ the structure similarity index measure at different levels to compute frame similarity. Then we set corresponding conditions to distinguish stack and moving camera shots. Next, in the case of moving cameras, point predictions based on TAP-IR are directly used as output results. For static cameras, we examine each frame and determine which things were moving and which were not. More precisely, we utilize the MOG2 to segment the counters of regions occupied by moving objects in each video frame. We trust tab IR for things that move and use static baseline for things that stay still. This helps us fix errors when things that should stay still seem to move. In our experiments, we only used the tab IR pre-trained model and did not need any extra data for training. We compare our method with others and we performed best compared to co-tracker and the original tab IR model. To analyze the contribution of each component in tab IR Plus, we conduct more ablation studies, and the results indicate that each component contributes to improvement. We also visualize the path of some points in the video using tab IR Plus. We observe that in the original model's predictions, some points went in the wrong position, but by identifying confident moving regions in the video, we are able to effectively correct the positions of most drafting points. That's the end of my presentation. Thank you for listening.
Is there any question? We might take one. I would have one question if the speaker can hear me. Could you tell us if the video is processed in a causal manner, like frame by frame, or does the model see the entire video at once?
Pardon, the voice is low.
So, does the model see the entire video from the beginning, or does it process it frame by frame?
I don't know what you mean.
Oh, sorry, I think we have a sound issue here because they cannot hear the sound from the room. Okay, we'll move on, and I'll take this question offline. Thank you again. So we'll now move to our next winner from the temporal action localization track. So hello. We have Xin Zhu.
Can I begin?
Yes, we can see your slides.
Okay. Hello, everyone. I'm Xin Zhu from the ICCV2023. I'm excited to share our solution for the action localization task. Let's now briefly discuss this task. For the TL task, the model analyzes a video to identify and categorize actions based on a predefined set of classes. The evaluation metric for this challenge is MAP. Significant progress has been made in developing deep models for TAL, such as React and Performer. Our approach can be divided into 4 main parts, namely dataset analysis, feature extractor, TAL, and post-processing. Based on the analysis of the PT challenge track 3 dataset, we observed that the training set was missing 3 category labels present in the validation set. To address this, we recorded videos representing these 3 categories and incorporated them into the training set to enhance sample diversity during training. To streamline the annotation process, each video was associated with only 1 action. In this work, we utilized the pre-trained model video MEV2 to learn a representation of videos that can extract valuable features for TAL. However, we found that this alone was insufficient. To address this, we transformed the TAL dataset into an action recognition dataset by parsing the JSON annotation file. Then we trained the standard action classifier by adding a linear layer on top of the pre-trained encoder. Finally, to capture the distinctive features of video clips, we utilize the VITB and the VIT large as backbones to obtain feature extractors. In this report, we use action formula as the baseline for TAL to predict categories and boundaries. We enhanced the model's recognition capability by increasing the head number from 8 to 32 and incorporating the FPN1D structure as compared to the baseline training architecture. WBF is widely used to merge prediction from object detection models. Inspired by the application in object detection, we have adapted the WBF method to suit the needs of the TAL task by considering bounding boxes as one-dimensional line segments. The approach involved training a model using features extracted from VITB, VITL, and a hybrid combination of both. To increase model diversity, the training set was sampled 5 times, resulting in 5 models for each feature extraction method and a total of 15 models. The evaluation results of these models were inputted into the WBF module, with equation feature weights assigned to each model result. This table shows performance compression of different features on the validation set of TAL. The final outcome achieved from the submitted system is recorded as 0.5. Finally, please allow me to make a summary. The approach involved augmenting training data, training action category prediction models, using pre-trained models and distinct backbone networks, and leveraging the action formula framework for the TAL task. The modified WBF enable effective fusion of test results. The achieved test set MAP of 0.5 ranked first on the leaderboard. That's all. Thank you.
Oh, Simon, can you still hear us?
Yes.
Okay. Tech is not a great, is not the strong point today. Okay, I see yours. Yeah. Okay, so unfortunately, I don't think we still have Simang online. But I have to say, I was really impressed that they actually filmed extra videos for the challenge. So we will definitely contact them to add those videos in the training set. So we will now go to the next speaker, who is in the room actually. So for the temporal sound localization. Can you connect yours? You want to- Are you on Zoom?
No.
He's not on Zoom. We'll just do it like that. Okay. Just
Hi, only for since the first offer is preliminary, I will speak quickly. Our solution is for perception test check sample style localization. First, I would like to have a brief introduction to the sample style localization task. In this task, the model receives a video which contains the corresponding audio and is required to localize and classify the sub-event occurring in the video. In other words, the model should predict the temporal boundaries and select the sub-classes from the predefined event set. As for our solution, we use a simple audio-visual fusion strategy. For the audio encoder, we adopt the base model, which is pre-trained on audio 2 million dataset, and the output of the transformer encoder is preserved as our audio features. For the video encoder, we adopt a mass teacher. This is also proposed by our team in ICCV, which is a strong video foundation model. And I will give the presentation in the Friday. Due to the similarity between the videos of perception test and something, we adopt a mass teacher large, which train on kinetics and fine tune on something or two, which provides robust video features. For the feature fusion, we finally adopt a simple early fusion strategy. It concatenates the audio and video features along the channel dimension. We also perform tempo alignment through video via video interpolation. In our experiments, such early fusion performs better than the late fusion. As for the localizer, we use the official action form baseline and training for 20 apples. We adopt the fuse audio visual feature as input, and the outputs are our final prediction. As shown in the leaderboard, our simple AI effective methods achieve the first place among the 10 teams. The MAP is 0.40, which is 7% higher than the second place. Okay, that's all about our simple solutions. Thanks for your attention. If you have interest with our other work, please scan the QR code. Okay, that's all I have. Do you have any question?
I think the same thing as for the previous track. We'll contact the author to get the features in our benchmark, because they seem to have very powerful features for both the sound. And we have Runze to present their solution based on Sevilla. Runze, can you hear me?
Can I share my screen? Could you hear me?
Could you put your slides up, please, if you can hear me?
We can hear you, but we can't hear.
Okay, perfect. We see your slides.
We can't hear him.
Okay. Hello, everyone. It's our pleasure to share our solutions.
We cannot hear you for the moment. Can you say something?
Could you hear me?
Check your audio. Now?
Could you hear me? Sorry.
Yeah. Can you speak now?
Yes, I
We
speak.
can't hear them.
Could you hear me? Hello?
Hello?
Ronzi, you can hear us, I assume, but we can't hear you at all.
Do we need to put the cable in?
But not in the next slides. No, we don't need the cable.
No, we don't need that. I'm not going to read that. Come on.
You want to put the next one?
Maybe let's try the next solution until we find a fix here. So we will, Hailing, if you're online, could you please try to present yourself for the grounded video question answering track?
And Ronzi, if you can leave the Zoom and come back, that might fix your audio because we can't hear you at all.
You hear me? You hear me?
Yes.
Oh, I can't share my screen now. Sorry.
Yes, go ahead.
Oh, sorry. You haven't shared your screens as yet. Can you share your screen? Oh.
No, I don't think this is working. Let's move to the grounded VQA. So
Yes,
which team is that?
VQA. And just KMG. Fabian,
yeah, can you please share your screen?
Sorry, there is something wrong with my computers. You can continue the next. Sorry, I will
Yes,
wait for another.
We're asking the next speaker. We'll see whether we can ping you in at the end. But the next speaker is? Yeah. Can we? Great. We can see some screens being shared. Can you try to speak? Internet has dropped in China. I think that's my.
It's just terrible.
Yeah. When is Rohit's talk supposed to be? When is supposed to be? When is Rohit's talk supposed to be?
45.
45 soon. No, we can't hear this one either. Oh.
Okay, we can see your slides. Can you speak?
Are they in the same room? Who's
Okay,
next?
that's a pity. Okay. So maybe we'll just try the next one, which should be the entry for the most novel submission in the point tracking task, Hanzang.
Hanzang, can you try to speak to check if we can hear you?
Yes, but I can't share my screen.
Fantastic, we can hear you. That's an achievement. Can you share you can't share your screen?
Yes, I can't. I tried, but the host do not permit the. I can't share my screen.
Please try now. We change the setting.
Okay, I can.
Yay, we see it.
Okay. Hello, everyone. I'm excited to present my solution for point shrinking task, titled Zero Shoot Single Point Shrinking with Point Feature Representation and Matching. This task is aimed to check the point through the entire video sequence. It has some challenges, such as shrinking arbitrary predefined points, dealing with potential occlusions, and we need to check the point along the entire video sequence. To address these challenges, we have employed a novel solution centered around a detect-free local feature matching model. We match the query frame with every subsequent frame in the video sequence. Here is a clipped video example. We select 12 points to show the tricky results. As you can see, we can achieve excellent performance for both static and moving points. However, as you can see, there are also some limitations when dealing with the occlusion scenarios. We use ResNet and FPN as our backbone. The inputs are the query frame and the subsequent frame. Through this backbone, we can extract multi-level features. The cross-level features are 1/8 of the original dimensions, and the fine level are 1/2 of features of original dimensions. After we extract multi-level features, we first flatten the cross-level feature and plus it with positional encoding. And then we interleave self-attention and cross-attention for 4 times. After that, we can got the transformed features. The attention layer uses the linear attention with 8 hands. After that, when we got the transformed features, we use a differentiable matching layer to get the cross-level confidence matrix. And then we first calculate the position I of every query point in the query frame. This is based on the input coordinates. It is important to note that for each query point position I, it corresponds to patch region of original row pixels. So once we obtained a position I, we need to retain the relative position in the name I's location. And then the predict J in the subsequent frame corresponding to the query point I will be determined based on the highest value in the name I's row. After that, for each query point I and point predicts J, we will crop a 5x5 window on the fine level features. Through the cross-profile module, we will got the sub-pixel level coordinates of predict J prime. Last, we add the retained relative position in the name I's location to predict to the coordinates of predict J prime. We will got the final predict coordinates. In conclusion, we use zero-shot learning setting for arbitrary point shrinking, fixed template query for each entire sequence, and fine-grained localization strategy via subgrid matching. And that's all my presentation. Thank you for your attention.
Do we have any question in the room? If not, I'll just say great visualization. We'll probably try to add that to our website as well. It's very nice. Thank you again for the presentation. So we will now move on to the second award for novelty. So the speaker is Linze for submission in the temporal sound localization track. Linze, can you hear me?
Yes, could you? Yes, I can hear you.
Okay. I'm Lindsay. Can you see my screen?
Yes.
Okay. Hello, everyone. I'm Lindsay. And I'm glad to share our approach for the third track and the fifth track, action localization and the sound localization tasks. Our team members came from Jiangnan University and the University of Surrey. In the third and fifth track, we are asked to utilize the video information and the audio information to localize and classify the action or sound events occurring in the video according to a predefined set of action or sound event classes. The annotation of each action or sound event includes the start and end types and the corresponding class. Its challenge lies in two aspects. The first is how to design a unified model to work on two tasks. The second is how to efficiently and collaboratively process video and audio modalities. To solve the mentioned challenges, we proposed the following pipeline: focal audio-video network called FAVNet. Video and audio cues have natural complementary qualities. So the FAVNet uses both video and audio modalities as inputs. Features are then extracted using the pre-trained video and audio backbone. In practice, to obtain more effective features, we extract video features using VideoMay 1.2 pre-trained on Kinetics 710. While for audio, we use the official audio features, which was extracted by the M1 Then the video features and audio features concatenate as union features. Then the three projections are used to process the different features and input to the temporal focal modulation, forming a feature pyramid. After the feature of the three modalities are fused at the decision level, the results are output by the classification head and the weighted treatment head. Inspired by FocalNet, we designed a more efficient temporal focal modulation mechanism instead of the self-attention mechanism in X-former to model the temporal information and the interaction between video and audio modalities. Different from FocalNet, TFM in FAVNet performs query interaction after aggregating temporal, video, and audio contextualization. Specifically, TFM consists of three branches: the TFVM, TFVAM, and the TFAM. Among them, TFVM modulates video and use audio as query. TFAM modulates audio and use video as query. And the last, the TFVAM modulation the union features and treats both of them as queries. Taking TFVM as an example, video features are linear mapped and then processed by temporal hierarchical contextualization and temporal gated aggregation. Audio features are used as queries to interact with aggregated features to fuse contextual information. Here are some experimental results on the test side. Our proposed FAVNet has a significant improvement over baseline. That's all my representation. Thank you for your attention.
Thank you. Since we're a bit late, we will continue without taking questions. But thank you very much for your presentation. We are really excited to see multimodal solutions for these types of problems. So we will make one more attempt to see if we can get the solution from the multiple choice VTA presented. Runze, could you please try?
Could you hear me now? Could you hear me now?
I can hear you. Could you please share your screen?
Oh, yes. Can I share the screen now?
Yes, please do. Dima, can you start?
Thanks.
Try now again.
Oh, okay. Um, could you see the screen?
I think it's coming. Yes.
So there is still something wrong with my screen. I just show the methods in this way. Hello, everyone. It's our pleasure to share our solutions in the perception test multiple choice video QA challenge this year. I would like to first introduce our team members. From left to right, our team members are Bao Yufan, Renzhe Zhang, Xiaochuan Li, Zhenghua Guo, Yaqian Zhao, and Rengang Li. Our team members are from Innsbruck, Tsinghua University, as well as Nankai University. I will introduce our work from the following aspects. In the multiple choice video question answering task, the model receives in parallel with the video a question and 3 possible answers, out of which only one is correct, and the model has to pick one answer. And during the challenge, only the train set data can be utilized. Therefore, the limited training data restricts the model performance. The questions cover 4 skill areas and require different types of reasoning across different modalities. In our view, the frequent action change may need the model to pay more attention to the temporal clues. We mainly adopted 2 methods to solve the above challenges. The baseline model we employed is the SEVR-LA model. We added a video Q-form module like Video Llama and pre-trained the model on the WebVID2 million dataset. Also, we found the pre-trained QVH dataset used in the original SEVR-LA paper may have a large gap compared with the perception test data. Thus, we enlarged the data combining 4 different sources of data besides the QVH data. We selected the similar things with the perception test data and retrained the localizer module of the SEVR-LA model. Also, we extended the original Flanty5 X-large model to the Vicuna 13 billion model. Besides, based on the findings, we designed a multi-stage training strategy. On the first stage, we added a video Q-form module and pre-trained model on the WebVID2 million dataset. On the second step, we loaded the model weights from the first step and trained the modified SEVR-LA model for the localizer modules with our combined dataset. On the third stage, we fine-tuned the SEVR model for the answer module on the train set of MC VQA data. Now it's our experiments. The results shown are all implemented on the validation set. The evaluation metric is the top 1 accuracy. We started from fine-tuning the SEVR-LA model and obtained 0.64 top 1 accuracy. Then we added the video Q-form module and boosted the temporal representation with the performance up to 0.65. We then put more attention to the localizer for accurate keyframe localization. We added more data and boosted the performance to 0.67. We changed the Flanty5 X-large model to Vicuna 13B model, and the performance went up to 0.685. We fused 10 more models and obtained 0.6 708 accuracy on the validation set. Finally, we tested our whole pipeline on the test set and obtained 0.715 accuracy. From our experiments, we sum up 3 points that can help strengthen the performance for the video understanding task. Firstly, the accurate localizer module is significant for the video understanding perception test. And secondly, the larger language models can help strengthen the reasoning task for the MCVQA task. And thirdly, the middle amount of domain data can help decrease the gap between the preaching data and the final fine-tuning task data. This is all about our solutions. Thanks a lot.
Thank you. So we don't have time for questions, but congratulations again for obtaining such an amazing performance on the task. And we hope in the future to see models that perform as well, but zero shot. So maybe we do one more attempt with the grounded VKA task. Hailing, could you please try to share your slides? Okay, we see the slides. Could you say something to see if we can also hear you? Unfortunately, I cannot hear you. Could you please try again? I think I heard something. Hey, Liang, can you speak now? Maybe it's a problem with sharing the slides in the same time as speaking.
Okay.
Okay, I can hear you. Could you try again to share the slides? So maybe don't go in full screen. Can you say something now? Okay, I cannot hear you. Okay, so unfortunately we'll have to move on to the next session. But we will ask all the winners to record their presentations, and we will post them on our website. So congratulations again to all the winners, and I'll invite Joe to introduce the next speaker.
So it is a great pleasure to have another offspring of CNU keynote today, Rohit. He will speak with the level of honor at CNU, lots of good work at national recognition, including one of the benchmarks that was an inspiration, the perception test, Peter dataset. He also did a super productive internship with us at DeepMind, where he had 2 papers, won the AVA challenge in 3 or 4 months. And afterwards, he joined Facebook, now Meta, now Gen AI, where he has been doing lots of great work on the multimodal learning, self-supervised learning. Welcome, Will.
All right. Hi everyone. Can everyone hear me? Hopefully on the Zoom and everywhere. Okay. Okay. Thanks, Joe, for the very nice introduction, and thank you everyone for coming to this talk. My name is Rohit, and I'm a research scientist at Meta. And today I'll be talking about some of the work I've done over the last few years in trying to evaluate perception models, and specifically looking forward to the next generation of perception models that we are sort of building now and will continue to build in the years to come. So just to explain what do I mean by these next generation of perception models, I want to think back to the kind of perception models we were building back when I was doing my internship and I was doing my PhD, which I refer to as the 2010s of perception models. So most of these models were very specialized. They were trained to do one thing and one thing only, and they did really well at that one task. I personally worked on video classification and sort of related problems, video understanding, tracking, and so on. And pretty much every time I was building a new architecture, and it did reasonably well at the time, at least, but it only did that one thing at the time. More recently, of course, there has been a bit of a shift in the kind of models we built. So we no longer train for just that one thing. So we no longer just train for video classification or just image classification. We're training these models on more general data, and then at inference time, using them to do a bunch of different things. And of course, I'm talking about models like CLIP, which are trained with web image text supervision. And at that inference time, you can use it to do classification, but also zero-shot classification or zero-shot object detection, or even use those embedding spaces to do image generation. And then more recently, we of course have models like Flamingo from DeepMind or Blip, which can go a step beyond and can even do captioning or generate open-ended answers for any visual perception task you might have. And then even more recently, we have models like CM3 Leon or GIL, which can, in addition to generating text, they can also generate images or other multimodal data and respond to your questions with even additional modalities. So while we have had this improvement in, or this shift in the kind of models we are building, where has the evaluation been? I would argue that the evaluation is still a bit in those 2010s. And here is the list of benchmarks that were used for example, the Flamingo paper. And you'll see sort of the same benchmarks that we have been using for when we were building our specialized architectures. And in fact, like I can see many of the data sets that I personally used when doing video classification, like kinetics and MSR-VTT and so on and so forth. And don't get me wrong, I do still think that it's incredibly impressive that we have a single model now that can solve all of these tasks and often solve all of them in a zero-shot manner or in a few-shot manner. So that is definitely very impressive. But in some respect, we are still sort of evaluating capabilities that we were evaluating back with our specialized models and not really evaluating some new capabilities that might emerge with the kinds of models we are training today. So what are these capabilities that I'm talking about? So one of them is this temporal reasoning capability. So this is something that has been going on for a while. So I was personally also looking at this back during my own PhD in terms of building video perception models. And as it turns out, even today, our existing state-of-the-art perception models still kind of struggle with that. And here is just an example from the perception test challenge that we have all been hearing about all today, where you can see that even sort of state-of-the-art models like Flamingo struggle to do temporal reasoning tasks. Whereas humans are quite good at those and can get almost up to 90% performance. The other limitation that I feel these models have is in terms of limited diversity of visual input. So this manifests mostly in terms of the kinds of benchmarks we've been using. So things like ImageNet, which are, of course, collected from a very specific collection procedure, which typically contains data from a certain part of the world and from certain viewpoints and so on. And this result from a recent paper called Geographically Diverse Evaluation shows that even for models like CLIP, they quickly start degrading as you evaluate them on data from different parts of the world. And then more importantly, even if you have different kinds of sensors like egocentric cameras and so on, you will quickly see that these models don't necessarily work as well because that kind of data is somewhat out of domain for the kind of data these models are trained on. And then finally, I think another limitation of these models is in terms of modalities. So while these models are multimodal, technically, they do have visual and text streams, so they can understand at least those two modalities. But they are still limited to just those two modalities. There are a bunch of other modalities that we might care about, for example, depth, audio, thermal information, and many of these sensors are now becoming readily available on our iPhones, on AR/VR devices, and we don't necessarily have those so-called foundation models for those modalities. And how do we, and in fact, finding data for those is also pretty hard. So how can we bring the gains that we have seen with these foundation models to those modalities which don't necessarily appear in the same frequency on the internet? And so that's what my talk today is going to be about. So I'll talk a bit about some of the work I've done in trying to evaluate these models temporally. And this was a work I did back during my PhD. So it's a few years old now, but I feel it's still kind of relevant to the kinds of things that we want our perception models to do. And specifically, I'll be talking about this work called Cater, which was a data set for temporal reasoning or understanding temporal reasoning in perception models. Secondly, I will briefly talk about this other work we did at Meta called Ego4D, which is similar to perception test. It's a benchmark for evaluating perception models. So it's actually both a training data set as well as an evaluation benchmark. And specifically, I'll be focusing on the benchmark aspect of this data in terms of evaluating perception models on this sort of egocentric domain where you have an agent doing actions and you have a viewpoint which is very different from the kind of viewpoint you typically see in ImageNet or other sort of third-person data sets that we typically evaluate on. And then finally, I will talk about this work called ImageFind, which we presented at CVPR this year, which takes these perception models to the next level by allowing them to be used with additional modalities going beyond just images, text, and videos. All right, so with that, let me get started with the temporal understanding aspect of it. So when we were developing Cater, our sort of main motivation was to design a task that required video to be solved. So this has been a sort of an age-old problem in video understanding where datasets like UCF, HMDB, kinetics have existed, but they're often solvable by looking at a few frames or a short clip at a time. However, if we think of general video understanding or how humans understand videos, we have tasks like this cup and ball shell game, where you have a ball under one of these cups and you basically shuffle these cups around. And the task at the end is to tell which of these cups the ball is under. And as you'll see, in this case, even a cat can solve these problems. And there are like a whole bunch of YouTube videos where you can see cats and other animals solve this task. Our video models, unfortunately, at the time at least, still struggle to solve this. And in fact, as it turns out, even today, they may not necessarily be that good at it. So inspired by this sort of use case, we developed this data set called Cater, which stands for Compositional Actions and Temporal Reasoning. So, so this was actually inspired from an earlier data set that came out called Clever, which was an image-only data set focused on compositional language and elementary visual reasoning. And it essentially added a temporal axis to that data set. So we had a similar sort of visual world. It's a synthetic data set rendered in Blender, and it had a similar visual world with a bunch of very basic objects. We added in one additional object called two additional objects, which is this cone and this little golden thing called snitch, which I'll introduce in a minute. But basically, it was these sort of simple objects, and we essentially just handcraft or just randomly selected some of these objects and moved them around at any given point in the video. So it was a fairly simple sort of generation process to generate these videos. And then we defined a bunch of tasks on it. And as you can see in these videos, being synthetically generated, you have a lot of control on the kinds of data that you can generate. You can add camera motion to it, you can add random lighting to it, and you can, of course, have as many objects as you would like. So now going over some of the tasks on Cater. So the first task we defined on this was the very basic atomic action recognition task. So this is inspired by sort of standard data sets like AVA, kinetics, UCF, and so on. And the task here was very simple. Given a video, classify which of these actions are happening in it. And we essentially had this exhaustive list of some 13 possible actions, which included like pick and place a certain object or a certain object containing another object. So yeah, one thing I should note is this one action that we had added here was containment, where this cone-like object can actually contain smaller objects. And in fact, this can be done recursively. So an even larger cone can contain that smaller cone. So that sort of action could also be done here. So that was the first simple task. And as you can expect, most of the models did really well on it. Then the first sort of more temporal reasoning task was this compositional action recognition task, where you had to, in addition to reason about the task, or in addition to reason about the actions, you had to reason about the ordering of these actions. So the classes defined in this case were basically pairs of actions as well as an ordering of them. So whether pick and place snitch happened before a pick and place cone, or any such combination like that, whether it happened before something, during something, or after something. And as you can imagine, this by definition now required some amount of temporal reasoning, because the first action could have happened in the beginning of the video, the last action could have happened at the end of the video. So you need to understand all of that all together to be able to answer whether this specific action happened in that order in this video or not. And then finally, perhaps the most interesting task here was this thing that I referred to as snitch localization. So the snitch here is this little golden object that you'll see in the back here. And in case you're familiar with the sort of Harry Potter universe, you would know that this is this object that you have to search for in the Quidditch game, and the team that finds it in the end typically wins the game. And here the task was exactly that. You had to tell where the location of the snitch at the end of the video. And it was defined very simply as a classification task. So we pretty much drew this like grid on the floor. So you'll see the little golden line here. And we just divided that sort of the floor into these 36 possible locations. And it was set up exactly like a classification task. You just have to tell where the snitch is at the end of the video. And while it might seem like this is a trivial task, you can just look at the last frame and essentially say where the snitch is. Just like in the cup and ball game, it can sometimes get a little bit more tricky. So if you look at this video closely and you track the snitch, you'll see that it gets contained by other objects, apart from, of course, moving on its own. So it can, of course, get occluded by objects, by things getting in front of it. But as you can see here, it kind of got contained by the purple cone, and then finally again got contained by this, this gray cone. So this is the final location of the snitch, and just looking at the last frame may not always give you all the information you might need to tell where the snitch is in the end, and that's basically the task. So given all these tasks, we evaluated some of the state-of-the-art methods at the time on this data set. And I won't go into all the details here because these models are a bit dated as of now, so may not be super relevant. But we evaluated sort of the state-of-the-art 2D models, 3D models, even non-local networks, which were sort of state-of-the-art at the time. And we basically found that performance overall on all of these tasks, or at least in the snitch localization and the compositional action recognition task, was relatively low. So this was clearly showed that the existing models at the time had this limitation in terms of temporal reasoning capability, and there was a lot more work to be done. Now, coming over towards the limitations of this method, the biggest one was basically that it was synthetic. And that, as computer vision people, we all know, we are not really fans of synthetic data, and that naturally meant this got much more adoption in the machine learning community than in the computer vision community, which I had originally hoped. But still, I'm glad to see that some of these ideas found inspiration in the perception test task, where you actually have a very similar task, which is now very real world. So if you hate synthetic data, you can definitely use a perception test task, which is also fairly similar, where you have to understand where the object is. So in addition to perception test, we have also been working on trying to build video perception models or long video understanding models that are now much more realistic and much more sort of real world, and the way or similar to how humans perceive the world. And to that end, now I'll talk a bit about this Ego4D benchmark, which has, again, a lot of similarities to what you've been hearing about with the perception test. So the motivation for building this Ego4D benchmark was that most of the computer vision sort of data sets relied on this sort of third person perceptual experience. And they were basically these sort of curated and disembodied moments and times from a spectator's perspective. And they weren't quite how a human would typically experience the world. Now, how humans experience the world is a much more sort of first person and egocentric perspective. So you'll see this person, for example, walking down in a supermarket, and you'll see a lot of camera motion, a lot of motion blur. And this is the kind of data that humans perceive, and presumably our future AR, VR devices will perceive, and also presumably our robotic systems will perceive. And this is a much more sort of uncurated and long-form multimodal visual data, and multimodal because these AR/VR sensors or other robotic sensors will have much more than just visual information. They'll probably have audio, IMU, and so on. And they're also no longer as curated, and they're typically driven by whatever the person is trying to do, which is their goals, intentions, and attention. So it's a very different kind of data set than what our typical visual perception models have so far been evaluated on. And just to give a sense of the scale of this data, it was much, much bigger compared to the existing data sets at the time. So here I'm just for reference showing Epic Kitchens, which at the time was the biggest data set, and this gray block is the largest data set at the time. Here the x-axis is the number of hours and the y-axis is the number of participants. And you'll see for context, Ego4D was much, much larger in both those axes. So this, of course, included both the training and the evaluation parts of it, but even the evaluation sets were fairly large and allow you to evaluate perception models in these new sort of visual environments. And these contained about more than 3,500 hours of daily life videos, over 900 participants, and most importantly, from around the world. So we had almost 70 plus worldwide locations, which, similar to perception test, allow you to evaluate your perception models, not just in the US or Europe, but even in like Japan or Singapore or India and Africa and so on and so forth. They were also not just grad students, they were people from all walks of life. So that gave you a much more diverse set of occupations. It was multimodal. And most importantly, we have benchmarks to hopefully catalyze research. And we have been running challenges, which I'll describe in a bit. So just to, again, drive home the point of the diversity, it was collected by this consortium of universities, which you can see came from all over the globe. So this gave us the geographical diversity that you often lack in existing visual perception benchmarks. And as I mentioned earlier, we had all kinds of different occupations also represented. So we had, apart from, of course, PhD students, there were carpenters, construction workers, landscapers, and whatnot. And also with different age groups. So it wasn't just like young students. Here is just an example video, which I'm sure many of you might have already seen. These are some of the videos that we have in Ego4D and which define sort of the basis of the benchmarks that I'll describe in a bit. All right, so going over the benchmark suite, we had tasks that spanned all different kinds of tasks that you might want to do with videos. So starting from understanding the past, we had this episodic memory benchmark where basically the question was about understanding where is X. So given this a video of the past of whatever you might have seen so far, the question was to answer, or the task was to answer questions like, where did I leave my keys? Or where did I meet this person last? So this, as you can see, is a long form understanding task where you potentially have to understand a long video to know where you last left your keys or where you met somebody and so on. Then, of course, we had some present understanding tasks, which involve things like hand-object interactions. This is your standard action classification setup where you're trying to understand what the person is doing now. Other present understanding tasks included audiovisual understanding, so audiovisual diarization, which is like who said what when, so understanding speech. And then also related to that was social interactions, which is who is looking at who or who's attending to who. And then finally, we had some future understanding tasks where, given the past, you had to predict what the person might do next. And this, again, you can imagine is a more temporal reasoning task because you might have to consider a long past context to figure out what the person will potentially do, given what they've been doing so far. And yeah, I'm just highlighting the ones which do require long temporal reasoning. So in addition to being geographically diverse and long forms, it also had these tasks which typically require some long form video understanding. We have been running challenges on this data for the last couple of years. And here I'm just showing some very basic statistics from CVPR, ICCV, from CVPR 2022, ICCV 2022 to CVPR 2023. And you'll see that we basically have been getting increasing sort of participation and increasing interest in these benchmarks, both in terms of number of teams that have been participating, as well as the number of methods they've been submitting, and specifically highlighting the specific tasks that I referred to as the more temporal reasoning ones, like episodic memory and forecasting, we are seeing quite a bit of increased interest. And we are hopeful that more teams, as they build even better visual perception systems, like the next Flamingo, Blip, or so on, will hopefully also give these data sets a chance and see how well their models can generalize to much more diverse visual input. And in case none of these benchmarks looked interesting to you, we also provide just basic text narration. So these are videos which are just narrated at a pretty regular interval with just general text narrations. And this allows you to, in addition to like train your models with this text narration, you can also define new tasks on it. And specifically, I would like to highlight this new benchmark that came out just a few weeks ago, I think, called Ego Schema from Berkeley. And this basically uses the narrations and the Ego4D videos to define some very hard temporal reasoning questions, which, as the authors show, cannot really be solved by just looking at a few frames. And in fact, the human performance here, again, is around 75%, whereas the best models, including intern video from Livin, who's here, is only about up to 32%. So a lot more, a lot of room for improvement, and hopefully the next foundation models can try to solve some of these tasks. All right, so with that, I would like to take a step forward and talk about how can these perception models be evaluated for multimodal tasks and going beyond just visual understanding or text understanding, which is the typical sort of setup for most of these visual perception models. So the motivation here, as I've been sort of mentioning earlier, is that we have image text data everywhere, which has allowed us to train these really powerful clip style models, which learn from this sort of large amounts of web image text supervision, and then can then allow or have enabled some impressive new capabilities like open set recognition, open set object detection. This is some work we had called Detect a few years ago. And then even these embedding spaces can also be used for generation. For example, DALL-E 2 uses the clip embedding space. However, what about all the other modalities that we might care about, like audio, motion, which is typically represented using the IMU output, or depth or thermal information? And many of these sensors are now quite readily available, but aren't really, we don't really have those so-called foundation models for these modalities. So our insight in this work called image buying that we presented earlier this year was to use images as the sort of universal language to bind all these modalities together and sort of bring the benefits of these latest next generation perception models to more modalities than just images and text. And the way we can do that is, and the reason we can do that is because images come paired with all these other modalities quite naturally. So images, of course, compared with text in the web text supervision that we have, but they also compared with depth information in outputs from a depth sensor like Kinect. They compared with thermal data and outputs from thermal sensors. And then they, of course, compared with audio in videos and with motion information like IMU and egocentric videos, because typically your AR/VR devices will have an IMU unit. And what this allows you to do is to learn this one single embedding for all of these modalities, such that they're all now embedded in this one space and effectively ends up connecting everything to each other. The way we do that is by starting with the representation for images, and specifically in this case, we use the clip embedding for images. We start from that and we freeze it. We basically use that as the fixed reference for every other modality, and then train an encoder for every other modality. So for example, an encoder for depth, an encoder for audio, IMU, and so on, and train that such that it aligns the features for that modality to the corresponding images for the data set for that modality, where you have paired, for example, audio and images. So you would want the audio representation to match whatever the corresponding little video clip would give you for that image, and the features are extracted using that fixed representation for image. So now once you map everything to this image embedding, you effectively get this sort of transitive alignment between all these modalities with each other. So now essentially text is now connected to depth, text is connected to IMU, and all of that allows you to do a bunch of new tasks, which I'll describe in the next slide, which previously you could not do when you were just training a model with just text and images. So for example, it allows for zero-shot recognition in all of these new modalities. The way that happens is that now that you have images that were already paired with text, so you have this association between text and images, and now that you have trained these short video clips with audio, so you have sort of this alignment between visual modality and audio, you implicitly get this alignment between text and audio, which now allows you to do zero-shot recognition for audio without ever having seen any audio-text paired data at all. So note that in training, we had no audio-text data, but by just aligning everything to this one embedding space, we can now do zero-shot recognition in audio exactly the same way you would do zero-shot recognition for images by just creating those templates and then just taking whichever is the closest in this feature embedding space. And to that end, we basically performed zero-shot evaluations on some of the standard tasks for audio. And these include audio set, VGG sound, ESC. On depth, also we did like NYU depth, sun depth, and also for thermal and Ego4D tasks. And you can see that image bind performed quite well, definitely much, much better than random. And in some cases, even outperformed the text paired setup where you had some data sets, you had that specific modality paired with text. Image bind was actually able to outperform that as well without ever having seen any paired data of any of these modalities with text. So this shows that it's in a very effective way to bring some of the advantages of these large web text data sets to all these other modalities and allows you to evaluate your vision text perception models on more modalities than just vision and text. And you can evaluate them for audio, depth, and so on. We also show that as you improve the perception model, so as you go from, for example, VIT base to large to huge, you see an improvement in performance even on these other modalities. So we all know that open clip, as you go from base to large to huge, you can you get an improvement in performance. But what this graphs show that even on the downstream tasks, or these downstream sort of other modalities that we are aligning to this original visual embedding space, you'll see that the improvement also improves here. So this basically shows that this can actually serve as a pretty good evaluation measure. So if you tomorrow have an even better clip model, you can basically do the exact same thing, and you can also evaluate its performance for example, audio classification or IMU classification and so on. And then finally, one of the very cool abilities that you get by having this one common embedding space is that you can upgrade any existing model, or you can evaluate your existing model, next generation perception model, with other modalities using this aligned space. So for example, let's say you have a really cool model that works with text. Now you can make it work with audio, for instance. And for example, I'll show, consider the model DALI 2, which is basically operates on the clip embedding space for text and then generates images. Now you can prompt that exact same model without any fine tuning or retraining using audio as input, because audio is now embedded in the exact same embedding space. And here are some results. And I'm guessing the audio is probably not playing or not audible. But yeah, basically the dog was barking, and then you can essentially generate an image of a dog. And here is another example. Okay, this is one. So yeah, with the sound of fire, you can basically generate an image of fire. And we have a bunch of examples on our website, so you can look over those. And in case you think that this is just limited to clip style models, that's actually not the case. And this is work from another group, not from our group, where they've actually brought the same sort of ideas to LLMs. And you can basically have a flamingo style model, which can also operate on image bind embedding space and can do all those cool things that language models can do, in additionally having other modalities as input as well. All right, with that, I would like to thank you. I know I'm a little bit over time, so thanks for listening to this talk. I hope I've motivated you a bit in terms of evaluating your next generation perception models and moving towards more temporal, more global, and more multimodal evaluations. Thank you. Yeah. Is there a mic?
Thanks for the talk. Like really nice to see the reflection of the past, now the present. I was wondering, do you think that maybe I will use a controversial word, but do you think that we are in the moment of like, if the symbolic doesn't pan out, it won't pan out then? Because I mean, we have been like contributing to the recent your work with we have been, now with the perception test. So we have like now a good software for things that work. So it looks like what it should work. I mean, the time.
I'm sorry, I didn't quite get what should work.
Neurosymbolic approaches.
Oh, okay.
Or symbolic based on the
Yeah.
guidelines.
Yeah, so I think that that's a good point. So there have been these recent works like Viper GPT or methods which kind of try to operate on some sort of symbolic representation of the world. So you would you take segment anything or something like that to give you like objects, maybe their semantics, and then build maybe a graph network or something on top of that. I think my sense so far is that our visual perception system isn't that great yet, or we miss a lot of things. So I don't think those. I mean, I think there are definitely a lot of promise there because they're much more explainable. You can explicitly tell you why it's making a certain prediction. But I think our visual perception methods still need some more work to give you exhaustively all the information you might need for the symbolic approaches to really shine.
That's what it is.
Yeah. I think we have a job for a few more years at least. Yep, that's a great question. And I didn't have time to go into those slides, but we do have some interpolation between modalities. So you can actually take, for example, the features for this image, which is this two birds on grass, and add this like audio. So this is audio of like waves, and then you can do retrieval on your data set, and you basically get images of birds on beaches. So it can basically combine those two semantic concepts and do retrieval with that. So so they are basically the same embedding space, and you can basically combine them as much as you would like. And we have more examples on our website.
Thanks for the talk. I'm more interested in the first works that are about vision planning. And something that I've been wondering is like how much sampling is important, like because I guess if you sample wrong, you might miss, I don't know, when the little ball was hidden. And I think it's something that maybe we sometimes we just take the significance that we're in, I don't know, IPD and stick with it. But yeah, I mean, what is your take on that?
Yeah, so I think like through video models, we look at every frame, the whole video, because that's what humans do. I mean, so there has to be some aspect of attention where you want to figure out which parts of the video are important and which parts are not. And this is something we actually did in my internship, where we had a model that could attend to certain portions of the video which were important and kind of like not focus as much on other parts which are not important. So for example, in Cater, the snitch might be the most important part, and you may not care about all the other like objects that are moving around, which are basically distractors. Of course, there is the efficiency aspect of it. Existing models aren't super efficient in doing this. So if you can do that efficiently, focus on the important part and like be able to sort of, track it over time, then I think that's pretty much how humans do it as well. And there's also the aspect of like event-based cameras and stuff, which represent sort of temporal information much better, but they haven't quite caught on yet.
Yeah, maybe I'll follow up. So the notion of importance is also, I mean, I guess it's relative to the task, right?
Yep. Yeah.
Maybe it just makes sense to maybe let the model know what the model is looking for in advance, or something to kind of have some motion.
Yeah, I think that's exactly right. And I mean, in this case, of course, the task you were only solving that one task at a time. And even for like perception, the next generation perception models, you can always prompt it with whatever you're trying to do. Maybe say find the snitch, and then the model should learn to attend to where it needs to attend to solve that task.
the temporal part, they mentioned that my input model doesn't really work well in temporal relationships. Do you think it's a matter of adding more modality so that finding a line between them, or is there another component needing amplified adding more and more modalities?
I didn't get it. So are you talking about the image bind work?
No, so in the very beginning, you mentioned that the file is being they're still not able to localize the actions very well compared to the cube. So what is like your maybe on this? We have just added more modalities and align them, and then the template will make different rules, or is there not a single component in the
Right. So I think with respect to temporal reasoning, I mean, modalities can have some impact. So I think audio can sometimes give you information that may not be visible visually. But in general, I think most of the visual perception models, like including Flamingo, aren't really designed to look at very long-term context. I mean, they do look at some temporal context, but it's still quite limited. And that's where, these long-form video understanding tasks like perception tests, these models start failing because, well, they just don't have all that information sometimes, or they aren't trained to look at that much information. Yeah. Yes. I think in the front.
So I think like to go for the interception test and some of the other movements works, I think offer fundamental new challenges. But naturally, like the first wave of solutions are kind of solutions that are designed for older challenges that people are trying out. So my question is, what do you think are the major new advances that would really be needed to make a bigger improvement on these kinds of tasks?
Yeah, I think that's a great question. I think I believe there are advancements in many different axes that can help improve performance on these tasks. So there's of course the temporal part of it, where you just need to understand like a long temporal video to know where, for example, the ball is in the end. Or for episodic memory, you need to understand where, or you need to have some sort of memory of where you last saw some things, or have some sort of memory of all the things that have happened so far. There is multimodal aspects to it. So actually, Dima gave a very nice talk a few days ago on how the sound information can give you things that you cannot even see visually. Like it can tell you about surfaces and certain actions for example, in egocentric view, you may not see, but you may hear them. So sort of incorporating all of those multiple modalities and having that long-term context, I think that should get us pretty far. And then I do think like how language models have moved towards, this one model that does everything. Right now, all our Ego4D challenges are usually solved by that one model that does that one thing and is completely focused on that one thing. I imagine that the best model one day will be a model that you can just prompt to solve a certain thing, and it'll basically solve that thing, and in addition to solving everything else as well, and hopefully do better than a specific model for that task. Yeah.
How do you separate between redundant modalities and complementary modalities? I'm guessing image bind is very much about the redundancy. If I can see this, I'll probably be able to do the other one the other way around, right? It's probably removing the complementary aspect of the modalities. And so does that worry you that there are like two aspects to the modalities?
Yeah, so I think depending on the task, you want complementary or redundant modalities. So like if you're fusing two modalities, you want them to be capturing two different things, like so that you get this additional performance boost by like incorporating them. Image bind actually is a way to make the other modalities also do things that one modality could do. And in fact, like once you have learned those representations, they are so similar that combining them is actually not a good idea. So yeah, image bind is not a good way to actually fuse two modalities, but more like make audio only work really well.
I'm a bit confused about how you combine IMU with the other modalities in the last point, because IMU first seems to be a property of the camera, not the scene. And also it's like a dynamics of the camera.
Well, here you don't mind that descriptors of starting by images, not in videos.
Right. So I think I maybe went over it a little bit too quick, but we actually consider images as well as short video clips. So when we align any modality to the visual part, the visual can be images or a little video clip. So the way we represent IMU is basically just the six numbers over time. So it's like a 6 times 1,000 or something sort of matrix. And that is the IMU signal, which we encode using a very small network. And then the visual input is basically a short clip that's encoded. And then you just map that. So each of these modalities are trained independently. So I mean, there's no real difference between if it's like a perceived modality or a camera property. They can all be embedded in that same space.
So some of the modalities you can see there, they're kind of like video modalities, like, I don't know, depth, thermal. So people even text and perceive video. So you think maybe we're like many modalities, it simplifies things a lot by just transferring many of them to vision.
Right. So depth. So you're saying depth is video because you can extract depth from videos.
Oh, don't you represent it as like in frames?
Yeah. So they're represented as frames, but I mean it's captured using like a Kinect sensor, or it's basically coming from a different sensor than the visual information. So I mean, I guess you could also extract depth from videos, and then maybe they are more sort of just a transformation of one to the other. But my understanding is that, like, for example, Ego4D videos, converting them to depth is like really hard. I mean, it depends on how well your SFM and like those things work. So yeah, I mean, as of now, there are like 2 different sensors, so we kind of treat them as a different modality.
The microphone is very good. You mentioned that you use a clip-based embedding for your images, but I mean, when you were mentioning the modalities, one thing is that the clip-based embeddings do not have the subtle details of the other modalities because they've been trained with text supervision sort of. So using that causes an issue. What would you use it for?
Yeah, that's a great question. That is an issue, but so far we haven't seen that to be a huge problem. The numbers and all, it still worked pretty well. I do think that a longer term, we might not want to start with clip because that's a very, like, it's limited to whatever the clip text and vision data have, and that's sort of what the embedding is capturing. Ideally, you would want to train a self-supervised representation like audio video and then sort of align everything to that. We tried that, it didn't work as well. As of now, I think the clip embedding is still much more than what a video audio embedding would capture. But yeah, I think maybe over time that might actually end up working better.
And going back to the of the I mean, slightly related. How far are we or like should we connect with the people doing computational photography? Because image finding, for example, why I mean you have multiple modalities, but they map to each other. So at some point we might also need to connect to design sensors, such that they are also easy to learn from. Right, and computational photography is like moving a bunch of image processing into the camera. So at some point, I mean, the learning, I don't know if we are far from it or.
I see. So you mean designing new modalities such that they are aligned to these?
Yes, sensors are easy to align or to learn.
I see. I think, at least from the perspective of image bind, as long as it comes paired with some image modality or some visual modality, you can very easily align it to the existing embedding space. So it's, I don't think there is anything specific that the sensor needs to do to be easier to align. As long as it can give you like a visual, corresponding visual output that's close enough semantically, then you can align it to the existing image bind embedding space.
Thanks, everyone. I think we need to move to the final section. So, thanks for.
Thank you.